Hey everyone, welcome. We're about to dive into something absolutely incredible, the science of optics. We're going on a journey to figure out what light is, from thinking about it as simple rays all the way to the truly mind-bending world of quantum particles. So, let's start with the big question. What is optics, really? Well, it's the part of physics that's all about light and how it interacts, or you could say dances with matter. And believe me, it is so much more than meets the eye. Now, I bet when you hear the word optics, your mind immediately jumps to things like eyeglasses, maybe telescopes or camera lenses. And look, you're not wrong, but that's barely scratching the surface. It's just the tip of the iceberg. What we're going to do today is take a trip through 3 revolutionary ways we've learned to see light. Each one unlocked a whole new layer of reality. So, prepare to see light differently. Okay, so let's jump right in with our first model. This is the one that's probably the most intuitive, the one that just kind of makes sense. It's called geometric optics, and it's all about imagining light as simple, straight rays. Yeah, this is pretty much the optics you learned about in high school, right? The idea that light just travels in a perfectly straight line until it bumps into something. Super simple, but you'd be amazed at how powerful this one idea is. This simple ray model, it works perfectly for explaining things like reflection, your face in a mirror, and refraction, which is that cool effect where a straw looks bent in a glass of water. It's the whole foundation for cameras, microscopes, even the glasses on your face. But there's a catch, a big one. This model totally falls apart when you try to explain why light sometimes bends and spreads out when it goes through a tiny little opening. That's a phenomenon called diffraction. And to understand that, our whole picture of light needed a radical update. And this is where our story gets its first big plot twist. We have to shift our thinking, moving from the big, large-scale world of straight-line rays down to the tiny, super intricate world of waves. You see, the very things that geometric optics just couldn't explain, like diffraction, are exactly what this next model, physical optics, was built to tackle. So now we dive into the world of wave optics, and this is where light starts to show us its more complex, almost fluid nature. Because here's the thing. Light doesn't always travel in a straight line. It doesn't always stick to the straight and narrow. Instead, it can act just like waves in a pod. It can bend, it can spread out, and it can even interfere with itself, creating these beautiful, intricate patterns of light and dark. The huge breakthrough on this came back in 1865 from a guy named James Clerk Maxwell. His now famous equations proved that light is actually an electromagnetic wave, like a ripple in the fabric of space-time itself. I mean, how cool is that? This was totally revolutionary. It unlocked our understanding of things like polarization. That's basically just the direction the wave is wiggling, and it's why your polarized sunglasses work so well to cut glare. And it also explained coherence, which is all about how synchronized and orderly those waves are. And you can see just how powerful that discovery was. Once we understood light as a wave, it gave us everything from the anti-reflective coatings on our phone screens to the absolute magic of holography. Oh, and also the fiber optic cables that literally carry the entire internet across the planet at the speed of light. But guess what? The story still doesn't end here. All right, get ready for the most mind-bending leap yet. We have to completely change our perspective. Again, this time we need to stop seeing light as a ray or even a wave and start seeing it as a particle. Welcome to the weird and wonderful world of quantum optics. So this wave model was amazing, but it hit a brick wall. There was this one thing it just could not explain, the photoelectric effect. Here's the deal. Wave theory predicted that any color of light, as long as you made it bright enough, should have enough energy to knock an electron loose from a meadow surface. But that's not what happened in experiments. What they found was that only light above a certain frequency, a certain color, could do it. It didn't matter how bright the wrong color light was. The math just didn't add up. We had a brand new puzzle on our hands. And the solution? Well, it came from a pretty familiar name, Albert Einstein, back in 1905. He came up with this radical idea that light isn't some continuous flowing wave. Instead, he said, it comes in these tiny, discrete little packets of energy. He called them quanta. Today, we call them photons. And this leads us to one of the weirdest, but also one of the most fundamental truths in all of modern physics: wave-particle duality. The idea that light is both. It's a wave and it's a particle. Which one you see just depends on how you decide to measure it. It's a completely profound idea, and it sits right at the very heart of quantum mechanics. And check this out. In 1960, this new quantum understanding of the photon led directly to one of the most transformative inventions ever, the first working laser. Here's the key insight, and it's so cool. Because light is a particle, you can have one photon hit an already energized atom and stimulate it to release a second photon that's a perfect clone of the first one, perfectly in sync. Create a chain reaction of that process, and boom, you get a laser. It's a device that literally could not exist without quantum theory.
So let's take a breath. Where has this incredible journey of discovery actually taken us? We've seen light as a simple ray, we've seen it as a complex wave, and now as a quantum particle. So let's put it all together and see how these three ideas are literally building our future.
This timeline really just recaps our whole story perfectly. You can literally see the dominoes falling one by one. It starts with the very first hints of light's wave nature way back in 1801. Then Maxwell proves it with math. Then Einstein comes along and reveals the particle hiding inside the wave. And finally, Mayman harnesses that quantum particle to create a brand new kind of light. You see how each step just built on the one before it? Amazing. And here you can see the legacy of each of these models so clearly. Geometric optics, that gives us the telescopes we use to look out at the stars. Wave optics, that gives us the fiber optics that connect our entire world. And quantum optics, that gives us the incredible precision of the laser. It's like three different models, three massive pillars of modern technology. And this really drives home just how deeply our understanding of light shapes literally everything. Our entire global communications network runs on light behaving as waves in fiber optic cables. Life-saving laser surgery depends on light behaving as particles, as photons. The next huge leap in computing, it might just run on photonic qubits using that same particle nature. And then you have something as awe-inspiring as the James Webb Space Telescope. It needs to use all three models just to capture those unbelievable images from the very dawn of time. It's just incredible. So the main takeaway here is that the science of optics isn't some dusty old chapter in a textbook. Not at all. From creating truly unhackable communication with quantum cryptography to developing brand new medical sensors, we are still just scratching the surface. We're only just beginning to unlock the full potential of light. And that really just leaves us with one final thought to chew on. This journey to understand something as basic, as fundamental as light, has completely reshaped our civilization, and not just once, but multiple times over. So it makes you wonder, right? What's the next big mystery out there? What's the next photoelectric effect that's currently baffling scientists? And when we finally solve it, what incredible new reality will it unlock for all of us?